Good morning, everyone. Today we will start with designing of Butterworth filters. Butterworth filter can be designed either with impulse invariant method or the bilinear transform method, but we will stick to bilinear transform method and let's see how it can be designed. The only difference between the impulse invariant method and the bilinear transform method is that the equation what we used for converting the analog filter equation to the digital filter equation. That means for HS to HZ transformation, whatever the equation we use, that will only change. Okay. So in the first question, we are given that the order of the filter is to the cutoff frequency FC is given by 1 kilohertz and the sampling frequency it is given by 10 to the power 4 samples per second. That means it is 10,000 hertz. Okay. Now from here, so whatever parameters are given, these parameters are for the analog filters. Okay. Now from here we need to find out the cutoff frequency, which is basically the digital cutoff frequency, and it is given by Fc equals to capital of Hc by Fs, which is given by 0.1 cycles per samples. So the values are given over here. You just have to put the values and from there you can calculate the small fc value. From the small fc value, we can calculate omega c, which is given by 2 pi fc, small of fc. So 2 pi multiplied by small of fc is 0.1, and from here we get 0.2 pi radians per sample. So this is the digital cutoff frequency of the filter what we want to design. Okay. Now using this equation, we need to calculate the analog cutoff frequency, which is given by omega c equals to 2 by t tan of omega c by 2. Okay. In this case, we need to calculate the capital T because our Fs is given here. Okay. This should be capital of F of S. So Fs is given. So from here we get 1 by 10,000. So if you put it over here, so we get 20,000 tan of omega c we have calculated as 0.2 pi. So 0.2 pi by 2. So from here we get the analog cutoff frequency of this one, 6498.39 radians per second. Okay. Now once you have got this one, you have to calculate the locations of the pole. Okay. How the locations of the poles can be derived? It is derived from this equation Pi, which is equal to plus minus omega c e to the power j capital N plus 2i plus 1 pi divided by 2n. Okay, and your I will vary from 0 to n minus 1. Now in this case, our n, which is the order of the filter, it is given as 2. Since the order of the filter is given as 2, we will just put the values over here as 2 and here as 2. Okay. So after you put this value, and break this. This is in the form of e to the power j theta. So we can break it down as in cos and sine terms. Okay. Now when you put the terms in cos and sine terms, then you have I which varies from 0 to n minus 1. So I over is 0, so P0 is equal to this one, omega c you already have, and from here you calculate this value. Okay. Then similarly, yeah, over here you are having 2i. So in the first case for P0 calculation, your I will be 0. Okay. So after putting all this thing, you get this equation, and then you get this one finally. So your poles P0, they are located at these two locations. Okay. Similarly, we will calculate P1 because order is 2. So we have to calculate Pi for I equals to 0 and 1. Okay. So for 1, in this case, in case of 2i, the I will be replaced with 1 and all other parameters would remain same, and omega c we will just put the values, and accordingly we get these values. Okay. So if you see, we are getting two values of P0 and two values of P1. Okay. Now from here we name it P01 and P02 and P11 and P12. So we have got 4 locations of the poles. Once we have got the 4 locations, we will plot these poles in the S-plane. So this is the S-plane. So we will put the values in this S-plane. Okay. Now in this case, what we will get? We are getting, see, P01, P02, P11, P12. So we have got 4 poles. 2 of them they are in the left hand plane and 2 of them are in the right hand plane. Right? Now we all know that we cannot place poles in the right hand plane, so we have to cut out the poles which are present on the right hand plane. So from here we will now deduce the analog transfer function. Now here the analog transfer function is given by omega c to the power n divided by s minus s1 multiplied by s minus s1 conjugate. So if you see over here, when you have calculated one pole, the other pole is the conjugate, is in the conjugate form. So what you have to put? You have to put the values of s minus the location of P01 multiplied by s minus the location of P11. Okay. So omega c, you know, order of the filter, you know it's 2. You just put in the values. So you get Hs something like this, and then in this Hs you will be putting S equals to 2 by T 1 minus Z inverse divided by 1 plus Z inverse to get Hz value. Okay, this one. So T we already have calculated from here. It is 1 by 10,000, and accordingly you start working. Okay. So this is the first type of question which you may get, where you have been provided with the order of the filter. Okay. In some cases, it might so happen that you are not provided with the order of the filter. Now what to do in that condition? In that condition, we will be given with the values of the modulus of h omega, and we have seen previously that in both in the pass band and the stop band there are some ripples. So our h of omega, it would vary in a certain range. So it is in between 0.8 to 1. So over here we are given with the normalized frequency response. That's why our value, it is varying from 0.8 to 1. Okay, and it is given that this is valid in the region of 0 to 0.2 pi. Okay, that means this is the pass band. Okay, and another value is given, modulus of h of omega, it is less than equal to 0.2 in the region of 0.6 pi to pi. So that means its value is much smaller than 1. That means it is the stop band. Okay, so first one is the pass band, the second one is the stop band. Here we can find out that AP, pass band gain, is 0.8 and pass band cutoff frequency is 0.2 pi. Okay, this is the cutoff frequency, cutoff edge frequency. Okay, pass band edge frequency, sorry, pass band edge frequency. Okay, similarly AS, gain in the stop band, it is given by 0.2 and omega S, stop band edge frequency, it is 0.6 pi. And here in this question t is not given, so we will assume that t is equal to 1 second. So our first step over here would be determine the specifications of the analog filter. Okay, so how do you find out? So we have to find out the analog frequency components, just like in the previous cases. So analog pass band edge frequency is 2 by t. We have considered t as 1, so it becomes 2. So omega p is equal to 2 tan of 0.2 pi divided by 2, which comes out to be 0.65. Now stop band edge frequency, similarly we can calculate, it is 2.75. Now we calculate these values in terms of omega p and omega s, and we just replace the digital frequency values with the analog frequency values, right? So we have now got this one. Now since the order of the filter is not given here, we have to calculate the order of the filter n. Okay, now the order of the filter n, it is given by 1 by 2 log of 1 by as square minus 1 divided by 1 by ap square minus 1, the whole divided by log of omega s by omega p. Okay, so we have already calculated as, it is given over here, ap we have calculated, omega s we have calculated, omega p we have calculated. We will just put in the values over here and we get a value of 1.3. But we know that the order of the filter, it cannot be in decimal points. Okay, it has to be number. Okay, so if I take order of the filter as 1, it will not work, because over here the order is showing that it has to be 1.3. So the minimum value should be 1.3. So whatever the value you will be getting, you have to take the ceiling value. Ceiling value means you round up. Okay. There are three things when you are rounding off. There are round off. Round off means less than 0.5, it will push into the lower value, and higher than this 0.5, 0.5 or higher than that, it will be push up to the higher values. Say if you are taking 0.5, it would be 1, and if it is 0.49, it would be 0. So that is round off. Okay. Then there is round down. In round down, what you will be having? Whatever the value, even if it is 1.8, it will be compressed to 2, compressed to 1, or round up to 1. And then the next one is round up, which is also called the ceiling value. Round down value, it is also called the floor value. Okay, it is also regarded as the floor value. Okay, so round down value, it is also regarded as the floor value, and round up values, they are also regarded as the ceiling values. Okay, so we have to take the ceiling values. So here our value is 1.3, so the ceiling value is 2. So we will consider that the order of our filter is 2. Okay. Now from here we will calculate the omega c. Now this omega c is given by omega p divided by 1 divided by a square p minus 1 to the power 1 by 2 n. Now again we know all these values, we will just put and we get 0.75. Now the rest of the procedure, it remains the same, right? See, it remains the same. Now here we have already calculated C, omega c. We know capital N values. Okay, so we just have to change the values of I and calculate different values. So over here we will be getting, again we will be getting 4 values. So P0, we are having this value. For P1 we are having these two values. So these 4 values are plot in this plane. So 1, 2, 3 and 4. So these 4 values are plotted. So we have discussed the pole values on the right hand side. We will cut and we will only take the values on the left hand plane, and we will calculate the HS. So after you have calculated the HS, you got HS values over here. So you have got the HS values from here. So you put the bilinear transform method. Here capital T is not given. We are assuming a value of 1. So we will put the value of 1 over here, and then from here you calculate, you get the exit value. Okay. So these are the two types of equations what we get in the Butterworth filters. Okay. So these are somewhat complex, this thing. So I would advise you to go for practice, and if you have any problem, then we can discuss. Okay. Do you have any problem? Anywhere you have not understood?
AP and AS, how we have to find it?
So
Yes, sir, that was
you see the
needed.
question, it's given over here. The value is 0.2. So in the stopman, whatever is the gain, that will be this thing, and for AP, it is the lower value.
Okay, sir.
Okay. and correspondingly the omega p will be given. This is the maximum distance, so this will be the passband edge frequency, and the stop band edge frequency, it starts over here, because when we are talking about the filters, it will be having something like this, right? So this frequency up to 0.8, so from here it goes down, so this value is a by root 2, right? I hope every one of you know. So this is basically the omega p, passband edge frequency, and similarly from here you get omega s. So the omega s over here is this one, 0.65. So this is passband edge frequency, this is stop band edge frequency. Sorry, this is not a by root 2, this is 0.8, and this is varying. A by root 2 would be somewhere over here. Cutoff frequency is somewhere, so over there your value will be a by root 2. Okay. So here it is just telling you that your amplitude values, it is varying between 1 and this is basically 0.8, the lower value, this is 0.8. So your amplitude values in the passband region, it is moving between 0.8 and 1. Anything else?
No, sir.
Okay.